The theorem I've written on the board is Rolle's theorem. Now, Rolle's theorem is a theorem that is actually quite important. And so Rolle's theorem and the associated mean value theorem, they're very important from a theoretical point of view. From the point of doing problems in the class, you won't see them that much. But it's important that we go through it just so that when you see the proof or an explanation, something that has Rolle's theorem, mean value theorem, you kind of know what those things are. All right, so that's the idea. So here's Rolle's theorem, and Rolle's theorem is very easy to understand what's going on. And you see, let f be a function that satisfies the following hypotheses, and these are hypotheses. The first two, very reasonable. You've got a continuous function on a closed interval. So we've talked about that before, right, with the closed interval test. We have the function is actually differentiable at all points on the open interval, so there's not like there's going to be any corners or anything weird, okay? And the value of the function is the same at the endpoints of the interval. So the conclusion of the theorem then is that there is a number c inside that interval so that there is a horizontal tangent, so that f prime to c equals 0. And that makes perfect sense, right? If you think about this, because of our hypothesis 3, right? So you've got this situation, say here's A and here's B. And here's F, right? This is f of A, but it's also f of B. So if I've got the same value here, well, one thing is the function could be constant. Well, which means that every point in between A and B has a horizontal tangent because it's a horizontal tangent line. The derivative of this is 0 everywhere. So that's like the obvious case, like the most simple case. But if instead your function actually moves somewhere, right? Here's A and here's B, it's the same point, same value of y, so if I go up, I better get back down, right? And if I go up and get back down, at some point in the middle, I'm going to have that maximum, and it's going to be a nice smooth maximum because my f is differentiable everywhere. Okay, so at that point, I'm going to have a horizontal tangent. Of course, it's the same idea if I'm going down, right? If I go down, but I have to come back up to that same value at b. So here, now there, I've got a horizontal tangent down there. And of course, this is only a statement of existence, not of uniqueness. And when it tells you there's a number, it doesn't tell you how many. There could be a whole bunch of numbers, right? Let me get rid of this case. It could be doing this, right? That's fine. This only guarantees us at least one. In this case, we have more. That's fine. Nobody cares. Okay? So the proof of this, which I'm not going to bother to do mostly because I don't think that it's of interest to many of you. I will, of course, give you a link for those of you who are interested. It's a very easy proof, though. It goes by cases. So basically you do, let me put the constant case back because that's case 1. Right? Constant case, there's almost nothing to do because at every point you've got that that derivative is equal to 0. And then you consider a case where somewhere you have f of x, which is taking a value bigger than f of a. And what you do, or in the third case, you assume that at some point there's a value which is less than f of a. And in either of those two cases, what you do is you exactly use the closed interval test, right? The mean extreme value theorem, right? We know that on this interval, because you've got a continuous function, you're going to have a maximum value and a minimum value, okay? And then, because it's a differentiable function, if it's actually not at the endpoints and it's in the middle, you're going to have you're going to end up with a critical point where the derivative is 0. So basically, that's the quick version of the argument. So really, it's entirely kind of based on what you see in these pictures, but we can actually make this argument because of the extreme value theorem.